out of the way, or if there's nothing there, then I can get there. So that's double deep, and of course triple deep would be even more dense. And the reason we do this, of course, is to store more product in the same general area. And so one of the issues that comes up there from a design perspective is this desire for density. We want to put as much product as we can in as little space as we can because the building is expensive. And that's a big issue in industry and something that real logistics companies are interested in. I have heard interesting demands put on warehouse managers, such as achieving densities at 85, 90%. We want 95% density, this sort of thing. One of the things you'll probably want to cover with your students is the difference between, there are different ways to speak of this, but sometimes I think what upper management means when they say that is, what fraction of the locations are populated? Okay, and the other way to think of it is, what fraction of the area is populated with a location, a storage location? So I could have 0 actual density here if I had no product in this, right? Okay. Right, very good, that's right. There is a third dimension, exactly. And so that's something else to consider. So it turns out a handy little result now I'm going to talk about the storage locations divided by the total area. This is a little result that you can kind of put in your back pocket that's very easy to understand, but it's sort of something you might not have thought of already, is that if I have a storage space with a maximum lane depth of k, so single deep storage with this would be 1, double deep would be 2, then the storage density is at most 2k over 2k plus 1. So in a single deep warehouse, it's 2k, that's 2, over 2k plus 1, that's 3. That says the storage density in this space can be no greater than 2/3. And by storage density, I mean number of locations divided by the total area. Here, it's actually 4 over 5, or 80%. And then you keep going at that 2k over 2k plus 1. And you can see the marginal benefit that you get for triple deep, fourple deep, fiveple deep, or whatever those other words are. Is that clear? Just a nice little formula that you can kind of get some judge of how many things can we put in this space. Okay, so that brings us to this question of block stacking, and I do this at both the graduate and the undergraduate level, if I teach this at the undergraduate level as well. And so I can't remember who alluded to this question. One of the speakers, I think Jim Apple. Yeah, Jim Apple mentioned this early, was if I'm in a block stacking environment, then I have to decide, well, how deep should the lanes be? And by block stacking, I mean I'm putting things on the floor, and then I'm going to create a lane of these things. It's the single skew. Then I'm going to pull them out. I'm going to eat through the lane, and then so on, right? So how deep should those lanes be? And it turns out this is a very well-developed area where we can compute very readily using some simple formulas, given some product characteristics that you see up here, the maximum stack height based on its weight and all kinds of things. I can actually just calculate what the optimal lane depth is for that SKU, okay? And it has to do with the demand rate and the usage of the area and so on, okay? Now the way this can be interesting in your courses is SKUs aren't the same, right? So I give them, for example, product data for, say, 1,000 SKUs and say, okay, lay me out a block stacking area. So one solution is I kind of do it for one lane depth for all SKUs. So you have to, just one lane depth in the warehouse. And then they get a total area consumed. Another way they could do it, the creative ones might say, oh, well, hey, I could actually segregate here and take the ones that want the really, because each individual SKU wants its own depth, its unique depth, so you might group them. Well, I'll let this group, I'll solve the problem for this group, and maybe those will be the deeper lanes, and then I'll solve the problem for this group, it'll be a shallower lane, and then you end up with some total area savings devoted to this storage area. So it gives the students an appreciation for customizing a storage area and allows them to do some analysis on smart design of block stacking areas to take up the lowest possible space in the warehouse. I'm not sure I made that clear at all. So this is what I was trying to say here. And this is an exercise you could give them. Product data for 1,000 SKUs, whatever you want. Lay out a block stacking area for potentially different lane depths. Make them do it for one lane depth first, and they can compute the optimal way to do that. And I'm going to show you, by the way, where all these formulas are here at the end of the talk. And then allow them to segregate and create product groups based on the characteristics of those products. And that's a nice little exercise for them. OK, so now a question, I'm getting actually all the way to the last question there, which was how do I arrange the picking and cross aisles in a storage area for my advantage? And so these are the designs that you pretty much see, some version of these in almost every warehouse in the world, where picking aisles are parallel to one another. And then a cross aisle, if it's inserted at all, will be generally about the middle. There may be 2 cross aisles, for example, at the 1/3, 2/3 points, roughly. Then perhaps more if it's a much larger area. These are pretty much what you see. And you can ask your students, do you see these in the grocery store, or get them engaged a little bit like that? Have you ever seen anything different? And in industrial warehouses, they'll say no. If they're thinking retail or grocery stores, sometimes they are a little bit different than this kind of design. You can ask them why, have a little conversation over that. But it turns out that these warehouses are based on 2 what we call unwritten rules of warehouse design. The first one is that those picking aisles have to be straight and parallel to one another. And the second one is that cross aisles, if they're present at all, they have to be orthogonal to the picking aisles. And warehouses since time immemorial have basically been designed to obey these 2 rules. And so you might ask them, does it have to be this way? And hopefully they would say, well, no, not really. And then you could have some discussion about, well, what would you do? And what I'm going to show you is the results of some research that we've done that relaxed these rules and came up with some new designs. So this is called the flying V. And the goal here is if I have, now let me give you the assumptions first. I'm not going to go through all the research that went behind this. But under the assumptions that every location has an equal probability of being visited. Okay, so random storage environment, if you know what that means. And I'm going to execute a single command cycle, which means I'm just going to start from a single pickup and deposit point from the bottom in the center. And I'm going to travel directly to one location, and I'm going to come back. So I'm not going to go make a stow and then go make a pick and come back. I'm not going to do that yet. Under those assumptions, this warehouse is about 10%. The expected distance to go get something is about 10% lower than it would be in a traditional warehouse. Even though it's larger because I had to insert this cross aisle. So this warehouse is actually larger than it otherwise would be, but it gives you that travel advantage. So you could talk a little bit about, well, would it be worth it to make the warehouse space larger if I get that travel benefit? Under what conditions would it be worth it? And you know, if you're visiting this storage area every month, this is not a good design. You don't want to, you've got no benefit. You got no payback. You want to get as much stuff in there as you can.
If you've got a zoned warehouse.
Pardon me?
If you've got a zoned warehouse, then each individual location isn't probabilistically likely. So
that's right.
The impact of zoning on this? Yeah,
and of course that would depend on what the velocity profile of the products looks like. Yeah, this warehouse turns out not to do very well in those kinds of environments. The one I'm about to show you does much better. Yeah. This is what we call a fishbone design, which basically takes this one. Now you notice there is a slight curve here. That's just kind of an interesting research result that we actually could not explain exactly why it's curved, but that's what the model produces. If I took these and I just flip them that way, you get something that looks like that. These cross aisles are straight. This is called a fishbone. It looks better if you turn your head like this. So I have an architect friend. I send him these 2-dimensional PDFs, and he sends me back beautiful 3Ds. He's got some software, some magic architect stuff. So you need a friend in that department. Or if you know how to do this, please let me know, because I'd love to be able to take 2D and make it into 3D very easily. And I don't know AutoCAD. So anyway, this is a fishbone. And it turns out that this warehouse, under those same assumptions and conditions, gives you a travel time benefit of about 20%. And so you could talk them through, well, is that appealing to you? Of course, that's appealing, but what are some issues with this warehouse? Well, I don't have any access to this from this side. That's a problem, right? And so you could talk about entry from other places and what are the potential disadvantages, that sort of thing. So here's a theoretical result that I showed them that shows this is a theoretical bound up here at the top. If I could fly like a bird from the pickup and deposit point to every location, what would my expected distance be? I'm sorry, this is percent improvement over a traditional design. Okay? So this is what that percent improvement would be if I could fly like a bird. That's the bound. This is what the fishbone design gives me for different height to width ratios of a warehouse. And then this is the flying V, which is inferior. About 10% for large warehouses and about 20% for fishbone. Any questions on that so far? Then I showed them this. This is a chevron. These are results from a new paper we've just put out. This is theoretically just like the fishbone, it turns out. Where in the fishbone, I travel up that diagonal and then either horizontally or vertically. Here I do the opposite. I either travel vertical or horizontal, and then I go up a 45 diagonal. So in fact, the expected results for this one are identical.
Minor question. When you're talking length to width, when you change this from orthogonal, how are you relating length to width? Is there something on one end or the other end that you call the length end?
So here, width to height, you mean that part? Yeah, so this would be the width. This would be the height. So 2 to 1 is, these are 2 to 1. Yeah, that's right. Yeah, I see your question now. Pardon me?
I think, yeah, okay, so you mean...
Oh, you're talking about this direction. No, yeah, I'm not doing this one all. That's right.
When you went to the fishbone, how does it matter? You could make that sort of square and then